Hello viewers, welcome to Big Boy Physics. In today's video, it's a lecture from constraint motion again, but it is the second part, and this part is devoted on the topic that is instantaneous axis of rotation on instantaneous center of rotation. Whatever you say. So this is basically a topic from the rotational kinematics, you can say, but I am taking it in kinematics so that we can do some other advanced problems of rigid body dynamics or motion of constraints in an easier manner, rather, you can say. Okay, so let's get started. So I have already explained about rigid body in previous video. Hope I do not need to repeat it again. I have taken a rigid body which is shown with the orange boundary. Now I consider 2 points A and B on this body. Now I consider that point A has velocity v1 vector along some direction, and point B has some other velocity, I'm marking it purple, that is v2 along some other direction. Okay, let me make it a bit tilted so that you can understand it properly. Now it appears that this body, if you view it from a certain point, it will appear that this body is instantaneously rotating with respect to that point. Try to understand. Basically, I mean to say that if you consider a point in the plane, there is a special point in this plane from which, about which, if you observe this body, it will appear that this body is rotating with respect to you. Okay, that's the magic in this concept of instantaneous axis of rotation. Now, how can you determine the instantaneous axis of rotation? That is the point or the axis of rotation. So what we do is that we draw two perpendiculars to the through the velocity vectors of each of the points, and the point at which they meet, suppose name them as point P. This point P is defined as the instantaneous center of rotation. Try to understand what I have done. Basically, along the velocity vectors, I draw two perpendiculars passing through that point, and the point at which they intersect is defined as the instantaneous center of rotation. So in this case, I'll say that P is the instantaneous center of rotation. Now with respect to P, this whole body will move with some angular velocity omega. Okay. Now let me say that this distance AP is equals to RA, and BP is equals to RB. Then we say that omega is equals to V1 by AP, which is V1 by RA, which is equals to V2 by RB. And that's the method in which we can find the value of the omega also. Okay. Now observe that if you try to write this as another form, you'll say that V omega can be written as V1 vector minus V2 vector. We write it in vector notation. Omega is basically a vector itself. So basically omega can be written as V1 vector minus V2 vector by RA minus RB. So RA minus RB basically represents the length vector connecting A and B. So I can say that this omega vector is basically my relative velocity of the both of the bodies with respect to the distances. Now relative velocity by the distances. Okay. So you might be wondering that this RA minus RB is not basically AB vector. You might have this question. Well, yeah, I'm just giving a raw understanding. So basically what we say that V vector is equals to omega cross R. This is the real definition of relation between velocity omega vector and R vector. Now VA vector can be written as omega vector cross RA vector. VB vector can be written as omega vector cross RB vector. So I can say that omega vector is equals to cross RA vector minus RB vector is equal to VA vector minus VB vector. Probably this equation makes sense rather than this one. So yeah, but in this case, observe that this V vector and RA vector, I can just put this to be perpendicular, क्योंकि omega vector is actually pointing out of the plane. Okay, you'll get in these details in the rotational motion also, or even we can discuss these rotational kinematics in this kinematics playlist itself. Okay. So basically, since omega vector is perpendicular to RA vector, so that is why we can write omega cross RA is equals to omega Ra. There's no harm in writing this. This is equals to Va. Okay. So yeah, this is the method in which we can find the omega of the whole body with respect to the instantaneous center of rotation, and we can also find the omega of this body. Now, what is the application? Application is, suppose we have asked to find the velocity of some other point C. Now, what is the velocity of point C? Point C's velocity will point out of the, that is perpendicular to the line CP, and velocity of C is written as RCP into omega. Omega is already defined from the previous equations. Okay, so that's the method which will be employing to solve the questions regarding rigid body dynamics, in which we can use the concept of instantaneous center of rotation. Now, there may be a question within yourself that if A and B both have velocities parallel, suppose the velocities of A and B are parallel. In this case, this is velocity of A and this is velocity of B. Then, does there exist any center of rotation? Yeah, necessary. It may not be there, but it may be there also. For example, suppose another point D on the line AP. Now this will have some other velocity Vd, but observe in this case that dp is basically greater than ap. So in this case, the thing is that velocity of d will be greater than velocity of a. So I can say that velocity of d is greater than velocity of a in this case. Hence, it's not necessary that these 2 points, if these 2 points have different velocity, they may not lie on the same plane. Okay, but yeah, if the both the points have same parallel velocities, suppose in this case, suppose consider 2 points, both have same velocities v. In this case, there we cannot define the center of rotation, because the body is basically translating, it's not rotating. In rotation, both of the points have different velocities if they lie on the same line parallel to the line connecting the instantaneous center of rotation and the point on the body. Okay, hope you get it. Now we'll be taking a question for better understanding. So सवाल तुम्हारे सामने. This question is taken from Jan Kalda. It says that a solid cylinder is attached to a thread and placed on a very rough friction conveyor belt moving with velocity. The conveyor belt is rough enough to prevent slipping. You have to find the velocity of the center of the cylinder. Okay, before going through the solution, before trying to give write the solution or trying to do it, you must know some concept that if a rigid body is there and it's attached to a fixed string. Okay, I'm holding it. Now if it unwinds, okay, the word is unwind means that it tries to go like this, then this point that is in contact with the string basically stays at the rest. Suppose in this case only, if the cylinder tries to unwind, then this point P is basically instantaneously at rest with respect to the thread. Okay. Similarly, now if I have a very rough surface and a body is placed here, it is moving. Okay, with some velocity v. Now, if it this body is very rough, then what happens is that this point P on the body and the adjacent point q on the surface, velocity of p will be equal to velocity of q. Okay, so that's the concept behind the very friction or no rolling case, sorry, no slipping case, but only rolling happens. Okay, so now give the problem a bit try, and then now pause the video and try for a few minutes, then look at the solution. Okay, going forward, I'm writing the solution. Now observe that I've already given you most of the hints for solving the problem. This point P in connection with the string basically can't move parallel to the string, otherwise the string will elongate. That is why it will have a velocity component perpendicular to the string. Let us represent it to be v1. Similarly, the bottom point, which is in contact with the conveyor belt, cannot move with the velocity greater or lower than that of conveyor belt's velocity. So it will have some velocity v1. Hence we can say that, sorry, not v1, it will be v, because the conveyor belt's velocity is given as v. So I can say that this instantaneous center of rotation will lie somewhere on the string, and the line perpendicular to the bottom point's velocity. Yeah. So here will be the somewhere the ICOR. Now to find the exact distance, exact omega, suppose this is the center, so I can say that this is the radius, this is also radius, and it's already mentioned that this angle is alpha. So by parallel lines theorem, we can say this will also be alpha. If I represent the ICOR by some point C dash, so I can say CC prime or CC dash is equals to R by sine alpha, right? Now the distance between ICOR and point of contact, that is P, so I can say C dash P is equals to R into 1 plus 1 by sine alpha. Hence I can say that omega of this body is equals to V by R into 1 plus 1 by sine alpha. Okay. Now they're asking me to find the velocity of point C, that is the center of the cylinder. So velocity of center C can be written as omega times distance of C from ICOR, that is omega by R omega into R by sine alpha, which will yield you the result, that is VC is equal to V by 1 plus sine alpha, and that's the resulting answer. Okay, that's the answer. Hope you get it. So that's the first problem of the video, and now we'll be taking up another problem, the second problem and the last problem. So let's get started. So taking the last problem of this video, this problem is from Pathfinder, and this problem is based again on the concept of ICOR and IOR. As usual, pause the video, give it a try for a few minutes, then see the solution. Okay, so let's get started. It says that free ends of two inextensible chords are wrapped on the massive disk of radius r is equals to 10 root 3, which are affixed to the ceiling at different points. Both chords and the disk are in the same vertical plane. At an instant after the disk is released, the angles made by the ceiling are theta is equals to 67 degrees and phi is equals to 53 degrees. Angular velocity of the disk is omega is equals to 5 radians per second. Now, what do you mean by angular velocity of the disk? Angular velocity of the disk means that the angular velocity with respect to any point. Now, this point can also be ICOR. One thing you must know, that about any point, you observe that the angular velocity will be same. The angular velocity will be the total velocity of any point is contribution of its angular velocity plus the translational velocity with respect to that point. Now ICOR is such kind of point which has translational velocity apparently to be 0. Okay. Now that's the thing which we'll be using in this question. Yeah. Now in this case they have already given omega, but few information, just a little bit of geometry is required. Consider this triangle. This is phi, this is theta. Now what is this angle? This is phi plus theta. Okay. So can you tell me the distance between the ICOR? I'm marking the ICOR as by the violet color and the center of the circle. So it will basically be that the distance from IOR or ICOR to center C is equals to R by sine theta plus phi by 2, right? So I can say that this velocity of center C is equals to omega times R by sine theta plus phi by 2. I just discussed about this formula a little later, once a little before. Okay, so that's the answer. Now just substituting the values, you'll get it to be 5 into what is radius 10 root 3 by sine theta plus phi by 2, that is 53 plus 67 by 2, which is root 3 into 2. Now observe that this R is given as in centimeters, so just multiply with another 10 to the power minus 2 in the numerator. Hence, the final answer will come out to be 1 meter per second, and that's the answer. If you are getting this as the answer, that is 1 meter per second. So, congratulations, your answer is correct. Okay, so that's it for today. We have discussed about IAOR and ICOR a lot, and I'll be coming up with more problems regarding these topics. Till then, stay tuned. Have a nice day. Good luck, and carry on with your hard work.